Hello, everyone. Today we're going to be going over section 1.2, which is going to be about variables, expressions, and equations. So we have 5 objectives today. We have our objective 1 is going to be evaluate algebraic expressions given values for the variables. Objective 2 is going to be translate word phrases to algebraic expressions. Number 3 is identify solutions of equations. Number 4 is going to be to translate sentences to equations. And number 5, we have what we want to distinguish between equations and expressions. So, beginning our section, it's good to just identify what a constant is. So a constant is just a fixed and unchanging number. So these are numbers we see in most cases here. So we have 1, 5, 3/4, 2.7, things like that. So normal numbers that we see, these are known as constants. Now, a variable is a symbol, usually a letter, and it's used to represent an unknown number. And sometimes we can see this being multiplied, divided, added, subtracted, any one of these things to a constant. We usually see them attached to constants, although we don't always have to see them attached to constants. But we do have here that variables or common variables are going to be x, y, and z, or a and b, but it can be any letter. So an algebraic expression is a sequence of constants, variables, operation symbols, and or grouping symbols such as parentheses, brackets, braces, or fraction bars. So what we see here for examples is we have something like x plus 5, 2y plus 3, 4a squared plus 2 times a minus 1. So these are just examples of algebraic expressions. So algebraic expressions are just any sort of combination of any one of these things to create some sort of expression that we see similarly below. All right, so our objective 1. We want to evaluate algebraic expressions given values for the variables. So evaluating an expression means to find its value. Since algebraic expressions can contain variables, we can assign different values to a variable so the algebraic expression can have different values. So if we ever have an expression and we see 1, maybe 2, any number of variables, we can fill in different values for each one of these variables, and we'll see our expression will equal different values, or they'll have different overall values as opposed to just with one value of a variable. So in our example, we have the expression 2x minus 9, and we're going to be using it twice. In our first example here, we're going to let x equal 7, and we're just going to see what our expression is equal to. So 2x minus 9, we're letting x equal 7, so we're going to place 7 in for x. So instead of 2x minus 9, now we're going to have 2 times 7 minus 9. Because remember, this 2x is like saying 2 times x. So now we have 2 times 7 minus 9. And using our order of operations, we know that 2 times 7 has to be solved first, and then we can subtract the 9. So our 2 times 7 is going to be 14. And we have 14 minus 9. And 14 minus 9 is going to be equal to 5. Now for our second example here, we still have 2x minus 9, but now we're letting x equal 10. So we're assigning a different value to x. And because x is just a letter, it can represent any arbitrary number or value. So we can be plugging in any number we would like for x. But for now, we're going to plug in x is equal to 10. So we have 2 times x minus 9. So now instead, we'll have 2 times 10 minus 9. Using our order of operations, we know 2 times 10 has to be solved first, which is 20 minus 9, and this is equal to 11. Okay, 11. So we see here we have the same expression, but when plugging in different values of x, we'll get overall different values of our expression. So our expressions, when containing variables, depend on the value of the variable for its overall solution. All right. And a word of caution from your book here. Whenever we see something like 3x squared, this means 3 times x squared, and it doesn't mean 3x times 3x. It refers you to example 1D, which is going to be in your book in section 1.2. Unless parentheses are used, the exponent refers only to the variable or number just before it. We would need to use parentheses to write 3x times 3x with exponents. So our 3x would need to be contained in parentheses with r to the power of 2 outside the parentheses in order to have 3x times 3x. If not, your exponent only follows whatever variable or number comes right before it. So that 3x squared with no parentheses is only really going to be equal to 3 times x times x. So just something to keep in mind. All right, objective 2 here. We have that we want to translate word phrases to algebraic expressions. When dealing with word problems, we have to translate phrases into expressions. And this is a common thing that we have with word problems, is that it's hard to set up an equation or an expression to go along with our word problem, since we don't exactly know how to translate it. But so we can work on translating these problems, or these expressions into word problems and vice versa. So we can have word problems into expressions. So as an example here, we have some phrases, and we want to translate these into expressions. So we have the sum of some number and 9. So let's identify some parts of this phrase before we just go ahead and jump right into writing out this expression. So first thing we have here is the sum. And the sum indicates addition. So we're adding values together. Some number indicates that we don't know what the number is, but we have to have a placeholder for it. So by saying some number, this is telling us we need to use a variable. And then we have and 9, and we know that's the number 9. So let's say our variable is going to be x. We can just make it x. So then what we have here is that we have addition of some variable x or some number x and 9. So this gives us x plus 9. And that will be our expression, since we have the sum of some number and 9. So our next example here, we have 16 minus a number. So minus, we know, is the minus sign. So this is subtraction. Then once again, we have a number, which is again indicating a variable. And this time, let's let this variable equal y. So we have 16 and subtraction with some variable y. So we can write this as 16 minus y. And I'm going to do a quick change of color here just to make a note. So I'm going to make it off to the side here so we have a little note. And this is to tell us that subtraction needs to be translated in order. So for example, this problem, we have 16 minus a number. So when dealing with subtraction, we have to go in order. And our order would be 16, then we have our subtraction minus a number. So we have to follow that order because it is not the same. 16 minus y is not the same as y minus 16. We have to keep the order when dealing with subtraction. With addition, it doesn't matter because our sum is the same no matter which way we flip our numbers. But that's not the case with subtraction. We can end up with different values if we mix up the order in our subtraction. So we have to keep the order in mind. All right, our last example here, we have the product of 3 and the difference of a number and 5. So we have quite a few things going on here. But so the first thing we really want to identify here, and what we're going to do is we're going to move this last line down a bit. So we have some room to kind of identify and point some things out. So we have the product of 3 and the difference of a number and 5. So if we're dealing with the products, well, that was ugly. Here we go. If we're dealing with the product is identified as multiplication. So this is multiplication. And if we're multiplying two things together, these two things are going to be separated by the word and. So we have the product of 3 and the difference of a number and 5. So we have a few ands here. But the key thing here is that our product is separated now by another phrase indicating another operation. And the difference is subtraction. So let's make this a different color really quickly. So let's make this blue instead. So we say our difference or subtraction is going to be in blue. And this difference, we say the difference of a number and 5, this and follows the difference because we're saying the difference between one number and another number. But our product is referring to 3 and this difference. So we have the product of 3, so we have 3 times this difference. Then we also now have here, and let's just put this in a different color since we are now identifying things in different colors. Difference of a number and 5, and this number is indicating our variable. And let's make our variable this time z. So we have this product of 3 and the difference. So our answer will be written out with a 3 times, and now we have the difference between two values. So when we write out the difference between our two values, we're going to write them in parentheses because we're multiplying 3 and this entire difference. So we're going to need some parentheses. And now the difference in question here is the difference between a number and 5. So it's subtraction, so we have to follow the order. And our order is telling us the difference between a number, so we begin with our number, z, and 5. So we have z minus 5. And that would be that answer. All right, so moving forward, when we think of translating these word phrases to algebraic expressions, the main things to remember here is that subtraction needs to be in order, and we also really need to pay attention to these other words like and. That's going to tell us what we are using our operation symbols for and how we are separating these symbols out. All right, objective 3 here. We have that we want to identify solutions of equations. So an equation is a statement that two expressions are equal. So for example, 9 plus x is equal to 13, 2x squared is equal to 18, 3/4 x plus 1/2 is equal to 0. So we have some expressions are going to be equal. Then we have an important note here is that an equation always uses the equality symbol. So whenever we see some sort of statement and it includes the equality symbol, that we know that this is an equation versus an expression. An expression doesn't contain the equality symbol, only operation symbols, constants, variables. So our equations have equality symbols and our expressions do not. So to solve an equation, we must find all values of the variable that would make the equation true. The values of the variable is or are solutions to an equation. So if we find some value that would make a statement with an equality symbol true, we know that that value is going to be our solution, or that value is the solution to the equation which we would need for that variable. So, as a first example, we want to decide whether the given value is a solution to the equation. We have 6p minus 1 is equal to 35, where p is equal to 6. So, we're given a value of p, and what we're checking here is that is this given value going to be a solution for our given equation? So, since we're given the value, we may as well check. This will be telling on whether or not it will be a solution or not, whether our equality symbol holds or if it does not hold. Holding in this case would just mean if when we plugged in this value for our variable, if we get the same number on either side of the equality symbol. So if we were to plug in 6 for p, this would give us 6 times 6 minus 1 is equal to 35. Using order of operations, 6 times 6 must be solved first. That will give us 36 minus 1 equal to 35. And we know that when we subtract 1 from 36, we do get 35. So we have 35 is equal to 35. And this is correct. Since it is correct, we can say p equals 6 is a solution to our equation. Our next example here is telling us 2m plus 3 is equal to 7, where m is equal to 3/2. So we want to do the same thing as before. We want to plug in these values. So we want to plug in this value of m and see if this equation is correct. So we have 2 times 3/2 plus 3 is equal to 7. When we multiply 2 and 3/2, this can become 2 times 3 divided by 2 plus 3 is equal to 7. 2 times 3 is going to be 6 divided by 2 plus 3 equal to 7. And we are going to run out of room, so we're going to continue this right over here. 6 divided by 2 is going to be 3, which gives us 3 plus 3 is equal to 7. But 3 plus 3 is equal to 6. So this actually does not work. So m equal to 3/2 is not a solution to our equation. And for problems like these, we can just plug in and check for our answers. All right, so on to our next objective. Our next objective here, objective 4, is that we want to translate sentences into equations. So what we're going to do here is we're going to write each sentence as an equation using x as the variable. So our first example here, we have twice the sum of a number and 4 is 6. So definitely some things to identify here. First thing here, we have twice the sum of a number and 4 is 6. So we have twice here. This means 2 times something. So twice is multiply by 2. And then we have the sum, which indicates addition, of a number indicating our variable, which is x, and 4, which is a number, is 6. And this is telling us equals. So we've kind of identified each one of our parts of our sentence here. So this twice means that we're multiplying by 2 this sum. And this sum we know is represented by a separate expression. But this means that we're multiplying this 2 by an expression and setting it equal to 6. So if we have twice, we multiply by 2. So this is going to give us 2 times the sum, so we're going to put parentheses around our sum, of a number, x, plus 4, is 6, which means equals 6. So our expression here is 2 times x plus 4 is equal to 6. Now our next example, we have 4 less than 3 times a number is equal to 8. So we have some things that are a little mixed up here. So we have 4 less than 3 times a number is equal to 8. So let's break some things down here. So we have 4 less than. Normally, when we have any sort of subtraction, we follow in order. But the key word here is that 4 less than something else. So this means that we're going to have this something else minus 4, because we're saying it is 4 less than this other expression. So 4 less than is actually going to be subtract 4. Then we have 3 times, which is multiply by 3. A number, which is our variable, x, is equal to 8. So we have is equal to, and we know that means our equality sign, 8. So, writing this out, we can't start with a subtract 4. Our subtract here and our multiplication are our operations. But when we have 3 times a number, that multiplication is solely for the variable x. Then we have our subtracting 4 is going to be kind of our main operation here. So when we write out our answer, we want to start with 3 times a number, which is going to be 3 multiplied by our variable x. So we have 3x, and then we have our subtracting 4 is equal to 8. Now, if we think about this, we have our original phrase, which was 4 less than 3 times a number is equal to 8. And our equation here is 3x minus 4 is equal to 8. And this is because when we have our 4 less than 3 times the number, we have to begin with 3 times the number minus 4 is equal to our answer. So whenever we have subtraction, we want to follow order, but our order in this case is a little bit embedded in our problem. So it's definitely also important to read into the word problem and try and see where that subtraction sign would go. All right, then lastly, we have our objective 5, which is distinguishing between equations and expressions. So an equation is a sentence. It has something on the left side, an equation symbol, and something on the right side. An expression is just a phrase that represents a number. So our first given example here, we have 4x plus 5 is equal to 9. So we have our left side, which is 4x plus 5, with our equaling sign, so we're solving it, and then our right side is equal to 9. Then our expression, which is just 4x plus 5, is our expression, and all we need to do is simplify or evaluate in this case. So I had said this earlier, but the key things you want to ask yourself when deciphering between an equation and expression is you want to ask yourself, does this have an equality symbol? If it has an equality symbol, it's an expression, and if it doesn't have an equality symbol, I mixed those up. If it has an equality symbol, it is an equation. If it does not have the equality symbol, it is an expression. I apologize for mixing those up there. Those E words kind of mess me up sometimes. All right, so if we have the equality symbol, it is an equation. If there is no equality symbol, it is an expression. So that's the main difference that we're looking for when we want to identify the difference between them. So in our example here, we're just going to go through a few different statements and phrases here, and we're going to determine whether it is an equation or an expression. So our first example here, and we're not solving these values or anything like that. We're just deciphering whether or not it's an equation or an expression. So our first example here, we have 5x squared plus 3 times x minus 1. Our question to ask ourselves, does this have an equality symbol? And in our first example here, no, it doesn't have an equality symbol. So therefore, it must be an expression. Then we have 4x plus 2 is equal to 10. Does this have an equality symbol? Yes. We have an equality symbol, which means that 4x plus 2 is equal to 10 is an equation. Then lastly here, we have 1/2 x is equal to 2y squared. We do have two separate variables here, but do we have an equality symbol? Yes. We do have our equality symbol, which means that this is also going to be an equation. You can also choose to think of it as an equation will have an expression equal to another expression. That is also another way to think about it. That finishes up our lecture on section 1.2 for today. So I will see you all tomorrow. So have a great day and I'll see you all then.